slotted line transmission line. We have seen in our previous study that along the transmission line there will be incident wave and reflected wave, and this incident and reflected waves will construct what we are calling standing wave pattern. And this standing wave pattern does not depend on the time, but it depends on the reflection at the load itself. So we can make use of such a standing wave pattern to measure the standing wave ratio, and from the standing wave ratio we can obtain the reflection coefficient, and from the reflection coefficient we can obtain the corresponding load impedance. This is effectively one of the earliest techniques in microwave measurements. Also, we have shown that such a standing wave pattern, the distance between two successive maxima equals to lambda guide over 2. And if we are assuming that the transmission line is air-filled, so the wavelength in this case would be the free space wavelength, which is C over F. So by measuring the location of successive maxima or successive minima, we can determine the value of lambda by 2. And from lambda, we can determine the frequency, because lambda is related to the frequency as C over F, and C is constant. So in this case, we can also measure the frequency or the operating frequency from the standing wave pattern. This can be done by using an apparatus called slotted transmission line. Slotted transmission line is actually a coaxial transmission line which has a slot, very narrow slot. This very narrow slot usually doesn't introduce a lot of perturbation of the electromagnetic waves inside the coaxial transmission line. This slot is used to add a very small probe, and this probe is connected to a small rectifier circuit. This small rectifier circuit rectifies the RF signal or the microwave signal to equivalent DC signal, and this DC signal is proportional to the amplitude of the electric field at the location of the probe. So if there is a standing wave pattern along the length of the transmission line, by moving the probe along the length of the transmission line, we can measure DC voltage varying in the same form of the standing wave pattern. And to measure the distances, usually we have a graded ruler attached to the detector here, and this grader and this ruler is attached with a variner such that we can measure fractions of millimeters. And here we have input port and output port. So the source is connected from one port and the load is connected from the other port. And according to the mismatch from the load, there will be standing wave pattern along the transmission line. By moving the location of the probe, we can determine the location of the maximum and the location of the minimum. In addition, we can determine the value of the maximum and the value of the minimum. And the ratio between the maximum and the minimum would correspond to the standing wave ratio. This is actually the basic idea of the slotted line. Now, if we measure the standing wave ratio, assuming that we have some load, some unknown load like this, and this unknown load will introduce such maximum amplitude of voltage and such maximum or such minimum amplitude of voltage. So by reading the value of the V maximum to the value of the V minimum, and take care, these values are DC values now. because these are the values after the detector, and the detectors effectively measure the amplitude of the signal. Okay, so this corresponds to V maximum and this corresponds to V minimum. By taking the ratio of V maximum to V minimum, we can obtain the standing wave ratio. From the standing wave ratio, we can obtain the amplitude of the reflection coefficient gamma. Gamma, or the amplitude of gamma, equal the standing wave ratio minus 1 over the standing wave ratio plus 1. But the reflection coefficient is actually magnitude and phase. So it is still required to determine the phase of the reflection coefficient. To determine the phase of the reflection coefficient, we should make a reference value, or we should take a reference value. And effectively, the well-known load which has a well-known reflection coefficient is a short circuit. So if we replace the load by a short circuit, the reflection coefficient of the short circuit is gamma equal minus 1. So in this case, the total voltage at the short circuit would be 1 plus gamma, so it would be 0. Now, after the short circuit, it would be maximum, minimum, maximum, minimum, and so on. And the minimum here, it would be 1 minus gamma, or 1 minus the amplitude of gamma. The maximum would be 1 minus gamma, 1 minus 1, it would be 2. And the minimum would be 1 plus gamma, 1 minus gamma, and so on. So, for the case of the short circuit, the total voltage at the point of the load is 0. And after lambda by 4, it would be maximum. And after lambda by 2, it would be minimum. And by adding another lambda by 4, it would be maximum, and so on. The advantage of the short circuit load is that we know exactly the phase of the short circuit. So, from the electrical point of view, the point where we have a minimum as a short circuit, this corresponds electrically to the same point of the short circuit itself, because we cannot make the probe exactly at the load. So we cannot put the probe here at the load exactly. As we have seen from the Smith chart, when we move lambda by 2, we return back to the same input impedance. So electrically, this point for the short circuited transmission line corresponds to the same point of the load itself. So this point corresponds to the point of the load. Or in other words, this point corresponds to the reference point or the terminal point of the transmission line. Okay? Now we have used the short circuit to determine the reference point of the terminal of the short circuit. We are going to move the short circuit and replace the short circuit by the load. For the load, we have obtained such a standing wave pattern. In this case, we can note that this is the reference point. This reference point does not represent or does not coincide with the minimum. Effectively, the minimum here for the load is shifted at another point. This point or this shift between the first minimum or the minimum of the terminal or the minimum of the short circuit to the minimum of the load is proportional to the angle theta of the reflection coefficient of the load, such that this minimum is related to the phase of the load as e to the power j theta plus 2 beta L, where L is the distance from the first minimum to the starting point of the slotted transmission line. And we said that this starting point of the slotted transmission line is determined by using the short circuit as a reference point. So this distance, after this distance, the total phase, it would be -1. And in this case, the reflection coefficient would be has a phase shift 180 degrees with respect to the incident field. So the total field would correspond to a minimum value. So the condition for the minimum value is that theta minus 2 beta L equals pi, or in other words, theta, the phase of the reflection coefficient, equals pi plus 2 beta L minimum, where L minimum is the distance or the difference between the minimum of the short circuit and the first minimum of the load. So we can obtain theta by calibrating the slotted transmission line by using a short circuit to determine the terminal or the location of the terminal of the slotted line, and then the distance from the terminal to the location of the first minimum. We obtain the length of the first minimum multiplied by 2 pi. We can find the angle theta. Now, if we obtain theta from the location of the minimum, and previously we obtained the magnitude of the reflection coefficient, we can find the complex reflection coefficient. The complex reflection coefficient would be the magnitude multiplied by the phase e to the power jc. By knowing the complex reflection coefficient, we can obtain the load impedance as Z load would equal Z naught multiplied by 1 plus gamma over 1 minus gamma. Okay? On the other hand, the frequency or the operating frequency can be determined as the distance from the first minimum to the second minimum equal lambda by 2. So by measuring the distance here, we can obtain lambda by 2, and from lambda we can obtain the frequency. So by using this very simple tool, we obtain the standing wave ratio, we obtain the wavelength, we obtain the frequency, we obtain the magnitude of the reflection coefficient, we obtain the theta or the phase of the reflection coefficient for arbitrary load, we obtain the input impedance of arbitrary load. All this stuff is obtained by a very simple tool which is called slotted line transmission line. Okay? As an example, assume that we have a slotted line transmission line, and we measure such a standing wave pattern for the short circuit, and it should be noted in the case of the short circuit the minimum is 0. And the maximum actually is twice the input or the incident voltage. And when we applied short circuit, we obtained the minimum at a distance Z equal 0.2 centimeters, Z equal 2.2 centimeters, and Z equal 4.2 centimeters. On the other hand, we replace this short circuit by an unknown load, and such unknown load we obtain such a standing wave pattern. It should be noted here the minimum voltage doesn't reach to 0, means that there is no complete reflection. And the standing wave ratio in this case would be the value of V maximum to V minimum. Assuming that the standing wave ratio in our case is 1.5 and the minima for this unknown load are obtained at the first minimum is obtained at 0.72 centimeters. The second minimum is obtained at 2.72 centimeters. And the third minimum is obtained at 4.72 centimeters. Now, from these results, we can say that the distance between two successive minima is 2 centimeters. Means that the wavelength would be 4 centimeters because the distance between two successive minima is lambda over 2. So lambda here is 4 centimeters. And assuming that, not assuming, it is air-filled transmission line. So in this case, the frequency of such wavelengths can be determined lambda equals C over F. So the frequency F is C, which is 3 multiplied by 10 to the power 8, over 4 centimeter, which is 4 multiplied by 10 to the power minus 2, it would be 7.5 gigahertz. So from the first measurements of just the location of the minima, I could find now the operating frequency is 7.5 gigahertz and the wavelength is 4 centimeters. That's what we are saying. The minimum repeat every lambda by 2. So the difference here is 2 centimeters. So lambda is 4 centimeters. So the operating frequency in this case is 7.5 gigahertz. Okay. Now we are going to determine L minimum of the phase. To determine L minimum of the phase, we are going to select one of the points of such minimum of the short circuit and assume that this is the reference point. So assuming that we have a minimum here at 4.2 centimeters, this point. So we are going to assume that this is the reference point. So we are going to make a line like this. So at this point, this corresponds to the terminal of the slotted transmission line. Now we are going to look at the distance from this terminal to the first minimum. So the first minimum here, after the terminal, it will be located at this point. So the distance from here to here, this will correspond to the value of or the length to reach to the first minimum. So the length to reach to the first minimum here would be the value 4.2 centimeters minus the location of this minimum. The location of this minimum is 2.72 centimeters. So 4.2 minus 3.72, it is 1.48 centimeters. And keeping in our mind that the wavelength is 4 centimeters, so by dividing this value over 4, this means that this value is 0.37 lambda. Okay? Now, if this L minimum is 0.37 lambda, the angle theta of the reflection coefficient of the unknown load would be pi plus 2 beta L. So this 2 multiplied by 2 pi over lambda multiplied by 0.37 lambda. So it is 4 pi over lambda multiplied by 1.48. Okay, here everything in terms of centimeters, no problem. So the angle theta in radian would be this value plus this value. This radian value can be converted into degrees as 86.4 degrees. Okay. On the other hand, the magnitude of the reflection coefficient gamma would be the standing wave ratio minus 1 over the standing wave ratio plus 1. So it is 1 minus 1.5 minus 1 over 1.5 plus 1 is 0.2. Here we have the magnitude of the reflection coefficient and the phase of the reflection coefficient. Now we can say that the reflection coefficient as a complex quantity is 0.2 e to the power j 68.4 degrees. Or in terms of real and imaginary, would be 0.2 cosine this value plus j 0.2 sine this value. Now z load would be z naught multiplied by 1 plus gamma over 1 minus gamma. By inserting this gamma, we can obtain that the load impedance in this case is 47.3 plus j 19.7 ohms. So by using the results of the measurement of such a slot line, we could obtain the wavelength, the frequency, the magnitude of the reflection coefficient and the phase of the reflection coefficient. And from the amplitude and phase of reflection coefficient, we obtain the input impedance or the load impedance. This calculations has been done numerically. It can also be done by using this Smith chart. How comes? First of all, we say that we have a standing wave ratio 1.5. And we said that the standing wave ratio corresponds to a real value on the real axis greater than unity. So on the real axis, we can move from the center to the point 1.5, this 1.4 and this 1.6. So this point is 1.5. So this point corresponds to the standing wave ratio 1.5. Now we can draw the constant gamma circle of such a standing wave ratio. Effectively, the load impedance would be some point on this constant gamma circle, okay, or standing wave ratio circle. It doesn't matter. And here is the voltage maximum and here is the voltage minimum. Effectively, the peak voltage of the standing wave ratio occurs at the point which corresponds to R maximum, and the minimum voltage occurs at the point R minimum. Okay. Now, after allocating such circle, we say that, okay, from the distance of L minimum, we obtain that L minimum is 0.37 lambda. So to move from the load 0.37 lambda to obtain we move from the load a distance 0.37 lambda to obtain the first minimum. And we say that the first minimum is located here. This is the first minimum. Alright? So the first minimum is located here. And we moved from the load, a distance 0.37 lambda to reach to the first minimum. Okay? So instead of moving from the load, which is unknown, we are going to move from the first minimum a distance towards the load. Actually, we don't know the load. Me, myself, I know this is the location of the load. But we know that this is the point of the minimum. Okay? So I am moving from the minimum towards the load, not towards the generator, towards the load, a distance 0.37 to reach to the load. I am moving from the first minimum a distance 0.37 to reach to the load. Moving toward the load is effectively counterclockwise or anti-clockwise. Here we see that this is the direction. I'm magnifying this point. This direction wavelength toward the load. So wavelength toward the load in this direction. And I'm starting from the minimum. So I'm starting from this point, which is 0. And I am moving a distance 0.378. So I am moving until to reach on this axis, which is the second axis here. The second axis, this is the first axis, and this is the second axis. I am moving until to reach 0.378. So I am moving here to reach to this point, and this point is magnified here. This 3.78. This is the point. And then from this point, I am extending a line from this point to the center of the Smith chart. The intersection of this point with the constant gamma circle will correspond to Z load. If I know that this is load, Z load, and I am moving from Z load the distance L minimum, I reach to this distance or this point. Okay? So the starting point here, I'm starting from the location of the minimum. And I'm moving from the location of the minimum a distance L minimum towards Z load. And to move a distance L minimum towards Z load, I'm moving counterclockwise on the outer scale, on the second outer scale, moving like this until I reach to the point 0.37. 0.37. Okay? And from this 0.37, I extend the line. The intersection would be Z load. Now, I could determine the value of Z load. How I could determine the value of Z load? From the standing wave ratio and the value of L minimum. So, in this case, we are going to read the value of R and the value of X. So, I'm going to magnify this point. This is the intersection point. The value of R is around 0.9 and the value of Gx is around 0.4. So, sorry, this is 0.95 because this 0.9 and this 1. So, this 0.95 and this 0.4. So, this is ZL normalized. By multiplying it by Z naught, so the value would be 47.5 plus J20. If we remember the value that we reached numerically was 47.3 plus J19.7, which is quite close to the numerical value. Okay, so this is how to use Smith chart with a slotted line to determine the load impedance of unknown impedance. Okay, all right.